Okay, let's start. So first we will have a basic review of numbers and functions, and to refresh your memory, and then we will learn more about this, about derivatives and integrals. We'll start with the notations. We'll set up the notations, what we are going to use for this course. So first, the numbers. We use this capital N, but put extra bulb there for integer, for natural numbers. Okay, is someone coming? Hey, hello, yes, come in, come in. Okay, take a seat. Mm. Just getting started. And what's your name? Okay, okay, okay. Sophia, when at school, when you say natural numbers, do you start as a 1 or do you start as 0?
1.
Okay, okay. But uh, there are two different conventions. Some start with 1, 2, 3. Some start at 0. Both are very popular. So when we say natural numbers, you should know what you have. Either you go with this convention or go with this convention. Then we have the real numbers, rational numbers. Then we have this real numbers. And then maybe in the future, we will introduce this complex numbers. Many of you have learned this before. So about the real numbers, have this real line. Okay. We have this real line. Then for every number, we have A, B. Then we have the notation. We want to use a notation to represent all the numbers between A and B. There are different ways to do this. Some use this empty end circles. A. So this is an interval of numbers between A and B. We have these different notations. A, B, the interval of the numbers. But this notation, it depends on the context. So we have a different setting. A, B. So the same notation, A, comma B, A, comma B. So it depends on the context. Do we mean an interval or do we mean a point on the plane? So this is an open interval. This is a point, and so we use R for real numbers. So this one has one coordinate, another coordinate. Sometimes we use the R squared for the plane. Okay, so whether this is a point or is this an interval. It depends on the context, depends on what we are talking about. Then we have this x, x. Sometimes we say this x stands for a real number. Maybe a represent is better. Or sometimes x is a real variable. Whether it's a number, a real variable, it depends on the perspective. Could be both. So there's some preparation. Then we move on to the first chapter about functions. So there are 4 ways to represent a function. We can use a description. You can say the area of a disk of radius r. An example. Or we can use a table. And list the values of the function. Can go a little bit better. We go to the graph. If we have the graph, can see the trend, whether it's become bigger, smaller of the function. Or we have a formula, an algebraic express formula. If we have a formula for the functions, then we can do manipulations. We can add them, multiply them. And these 4 different ways of functions. We can go back and forth. We can go from the description to the table of values, to the graph, to the formula, can go back and forth. Okay. Then about the function, we use what is a function? Normally we use this. So this stands for the domain, where the function is defined, and this is for the range. What are the values of this? We give a point in the domain, we assign a value. Okay. So sometimes functions have the same formula. Yes. They may have the same formula, but if we change the domain, we will view them as different functions, a different perspective. So if we go y, this is also very popular. In this one, f is the function. And x is the independent variable. and y, it's the dependent variable. Independent variable, we can change x freely. The dependent variable, when x changes, y changes. The change of y depends on the change of x, the dependent variable. If we pair the information, we get the graph. So here you can see this is represent a point. It's not an interval. So it depends. This depends on the context. In this context, it is a point. And some very basic functions. Maybe I start with Sophia. Give me an example, a very basic function. What function would you give?
Y equals X.
Okay, that's the first one. How do you say your name? Sakina. Okay, give me another function. Okay, that also works. Okay. So for these two functions, the domain, they're all real numbers. Okay, Sophia, what's the range of your function?
Negative, all real numbers.
All real numbers. Okay, negative infinity to infinity are all real numbers. Sakina, what about your range? Okay, so 0 to infinity. Domain and range. So now give a function, we can find the graph of the function. The graph will be a curve in a space. The first one, the graphs are curves. On the other direction, if you give a curve, is the graph of some function. Okay, Sophia, what's the answer to this one? Yes or no?
Uh, no.
Okay. You can keep yourself unmuted. You don't have to mute because it's very quiet. If there's noise, you can mute. If there's no noise, just leave it. That's easier for us. Okay, so your answer is no. So do you agree? Okay, examples? So examples, some curve that is not a graph. Circle that work? Okay, okay. So if we have a circle, uh-huh. Okay, okay. So what you mentioned is the vertical line test. The vertical line test. But this one, let me see if I can switch this. So as we move, oh, she cannot see this. Only I can see it. Mm. So if we draw a line, this line intersect the graph at one point, this graph at one point, the vertical line test. But for this one, if we draw a line, it intersects at 2 points. So that's the vertical line test. For the curve to be the graph, it can only intersect each vertical line at one point. Okay, very easy. The next one, piecewise defined function. So for the previous functions, we have the one formula for the whole domain. But sometimes we have a different formulas for different domain. Like for example, okay, so for this one, if x is negative, we define as the square. Positive, we define as the x itself. And we can try to graph it. Okay, a very useful example, a very useful function, the absolute value. Absolute value. Okay, I think you have seen this before. Sophia, can you describe the graph of this function?
Um, so it's like the graph of the function x equals y equals x
Mm-hmm.
on the
So
right,
yes, yes.
and then on the uh, on the right,
Mm-hmm.
including 0, and to the right of that, and then to the left of that,
Mm-hmm.
it looks like the graph of y equals negative x.
Okay, go this way. Okay. Okay, now I want you to have a piece of paper for the graph, the following three functions. This one. Graph. and their difference. Okay, for the graph, there's three functions. Yes. Hello? Okay, Sophia, how do you graph the first one? X minus 1, then absolute value. Is it similar to this one? Huh?
It transformed the whole thing one, right?
Okay, okay. Because when X is 1, this is 0, so we translate this to the right by 1 unit. Okay. Begin, what about the second one? The left by 1 unit. Okay,
Yeah.
okay. And the second one. Okay, now let's see what's the difference? What would you say about the difference? Okay, so let's start using to graph this directly. Let's break this into 3 pieces. I want to break this. Okay. When x is less than -1, the value of this one is this. The value of this function is this. So can the difference. So from here, this one subtract this one. It's a constant difference too. At this point, when x is -1, so this will be 2 minus, I'm sorry, so 0 minus 2. You can see -2. Okay, Sophia, what happens if x is bigger than 2? If x is bigger than 2, what this one? If let's say x is 1, x is 1, what's this point? What's the value of this one?
Uh, that's 2.
And this
0,
difference?
2.
Okay, so if it's bigger than 2, we get this. So in between, we can simplify this, but what the result is from. Okay, so that's the graph of this function, the difference of two very simple functions. But these two very simple, but the difference kind of different. And in fact, we can get a formula for this. So the piecewise defined function, we have a formula for this. The difference, -2 and 2. And in between where x is between -1 and 1, this one will be positive. So x plus 1 is positive, so it's x plus 1. X minus 1 is negative, so the absolute value will be negative. So this becomes x minus 1 . Okay, so we have a formula for this. Again, it's a piecewise defined function. A very popular function. It's in engineering, in physics, it's called the unit step function. Very simple, but very popular. It's like with the lights, like the light, initially it's off. We turn on the light at time 0, so like a switch. Okay. Then about the function, we also have some properties of the functions. Symmetry. So first, we consider the function defined on a symmetric domain. If the domain is not symmetric, we will not talk about the symmetry of the function. To talk about the symmetry of any function, the first requirement is on a symmetric domain. Okay, many of you have seen this before, the even function. Odd function. Okay, Sophia, give me an example of even functions.
Y equals x squared.
X squared. So Kina, odd function. Simple ones. What about this x cube? It's even. Okay, the very simple one, x cube. Okay, now both of you, could you give me a function that's not even, not odd?
Y equals square root x.
Okay, very good. Okay, very good. But let's see why. Why you say it's not even, not odd, Sophia?
There's The domain is only
Mm-hmm.
from 0
Very
to
nice.
infinity.
Okay, so no symmetry because the domain is not symmetric. Okay, now another one. Could you give me a function that is both even and odd? Any function that is both even and odd. Well, it's not easy to find an interesting one because in this case, the only function is a zero function. It can only be zero. The reason for this is because it's an even function, it is fx. Because also an odd function is negative fx. Now the number equal to the opposite, it can only be zero. This implies okay. Uh, so now we will go to the next subsection about models. So elementary functions. Okay, the one we have seen before, x, x, x squared. And more generally, we have the quadratic function. We can add one more, x cubed. Then we go to the cubic function. Even more generally, go to the all polynomial. So this is polynomials. And this x is the variable. And this a I, a1, a0, a2, the coefficients. Okay. Slightly more general is the power function. The a. So here a is a fixed number. In a special case, when a is a positive integer, that's something we just introduced. And negative integer, maybe fractions. In this case, it's called the nth root. But for this one, there's some ambiguity about the function. Do we allow negative x. So x 1/2 some rotations cubic root and the nth root. For the square root, we say, okay, the x cannot be negative. Okay, that's very common. But for this one, do we allow again, this is a choice. Sometimes some people allow this and some people don't allow it. It depends on who is teaching the course. Okay. For me, I would discourage this. This is not encouraged, may not recommend it. So whenever we deal with fractional power, we only allow positive number. So that's my recommendation, x has to be non-negative. Okay. And the negative number, we have learned this before, the reciprocal. Okay. And the rational functions. Reciprocal functions. A typical example here. Okay, so for this function, what's the domain of this function, Sophia?
It's 1 to infinity.
And okay, that's part of the domain. So here we want x squared to be positive x squared. Now, so it's either bigger than 1 or less than -1. Okay, so that's the domain. Another function, another class of function that we will use is the trigonometric functions. The most basic ones. If the side is 1, this will be this leads us to the trig function. So again, have you seen these two functions before? Sine and cosine. Okay, very nice. And there's a very important formula for these two functions, called the formula of angle addition. Okay, Sophia, could you recall the formula for these two? Do you,
Sine
Okay.
Cosine y mi- plus minus cosine x sine y
Okay.
times.
Okay, very nice. Okay. So this is the formula for angle addition of sine. So Kinder, do you know what's for cosine? It's similar but with some differences. Okay, very impressive. Okay, so if you know these two formulas, it will be much easier when you learn the properties of the trig functions. Okay, so the last one is the tangent. But definition is the ratio. So for this to be defined, the domain, cosine cannot be 0. So x is not. So a simple domain will be on this domain. The graph looks like the next section about functions from odd functions. Okay. So again, we'll go over this very quickly. Fx plus c. Okay, this represents a vertical shift. This one, so it's a horizontal shift. However, when c is positive, the shift to the left. For example, we shift the graph to the left. Okay. And we can add, multiply functions. Addition. Two functions, we can add them. And the multiplication. We multiply the numbers, get a new function. A new operation for the function is the composition. Given two functions, we can compose them if the domain matches. And we introduce a notation for this, f compose gx. So it defines a new function. Okay, let's see some examples. So fx gx. Let's find f compose gx and g compose fx. Okay, tell me what your answers are. Sophia, how do you find this compositions?
You um plug in x plus 3 into
Uh-huh.
x, so you like replace it with x, so
Okay.
it becomes x plus 3 cubed.
Okay. Okay. Kina, then the next one. X cubed plus 3. So this will be g fx g. Let's try f compose f, g compose g. Sophia, what's the first one?
Uh, x to the power of 9.
Okay, so this will be f fx so can the next one? Okay, okay. All right, we move to the next section, 1.4. It's a review of this exponential function. Okay, we start with a special one, 2 to the x. We compared with x squared. So this time the variable is on the power. This variable is the base. So this is the power and this an exponential function because the variable is the exponent. Okay. So we can graph this. More generally, we have fx for any base. So here we assume b is positive because when b equals 1 is a trivial function. So normally we require b is not 1. Ah, not 1. Loss of 3 loss So here we will assume that A and B, the bases, are always positive. And the exponent, it can be any real number. We should be very careful. If we allow negative bases, some of the laws will fail. Mm, 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 mm. Sophia, have you seen this before?
Uh, I think so.
Okay, so a typical example is A equals B equals -1. X equals 1/2. A typical example for this it will be -1, 1/2, -1, 1/2. If we can apply the laws, if applicable, so this give us -1, but if we apply the third law, third law tells us -1, -1, 1/2, 1. Oh, so here I missed a number, let me correct it. Erase. Okay, so if we are being a little bit careless, if we allow negative bases for fractional powers, so here we apply this law because it's the square of the same thing. We get a -1. We apply the third law for the same thing, we get a 1. Okay, Sophia, what would you say about the reason for the differences?
Uh,
One, if we apply this law, but -1 if we apply the third law. Skinner, what do you see? Uh-huh. Okay, so now about this quantity, should it be -1 or should it be 1? Which one is correct? Well, so here, so the question about this, because it goes beyond the domain of these formulas. So these formulas apply on this domain, AB positive. Here, if AB is negative, it goes beyond the application of this. So here we should say these formulas not applicable in this case. So the reason is the reason for this disagreement, the formulas not applicable. AB and XY fraction. Okay, so we apply a formula to know when it's applicable and when we cannot apply the formula. So this is one example of this. Okay, and so so here we have a special case when x equals 2. Another one, x equals 3. Let's try to graph that one. 3, if it is 3 over there, 3 is 1/3. Okay, so then we check the tangent line. This one, we compare the slope of the tangent line for 2 to the x. Now we can compare the slope of the tangent line for 3 to the x. We compare it with the diagonal. You can see for 2 to the x, the slope is less than 1. 3 to the x, slope is bigger than 1. So there is something in between where the slope is exactly 1. So comparing the slope. 2 to the x, slope less than 1. 3 to the x, slope bigger than 1. So both at x equals 0. So because of this, we can find a number here unique in between. So this number, Euler gave it a name for E. So we call it the natural exponential function. Sophia, have you seen this number before? What else do you know about it? Do you have an approximate value for it?
As x approaches infinity, um, um,
We know it's between 2 and 3.
um, I forgot.
Okay, that's okay. I just should try to refresh your memory. Sakina, have you seen this number before? Do you know other stories about this? So there's another mathematician called Bernoulli. Okay. So he kind of discovered the same number when he studied this continuously compounding interest. Yes, compounding. A very useful subject. Maybe we'll come back to it later. So at this moment, we will go to the next section about the inverse function. And from there, we will introduce logarithmic function. Okay, so previously we have the vertical line test. Want to determine if the graph is a function or not. Now we have the horizontal. So this is whether it's a function. But this, whether it admits inverse functions. What does this mean? Maybe you have seen it before. Sophia, have you seen this before?
Yeah, it's like
Okay,
one-to-one function.
okay. Sakina, what about you? Okay, so it's for one-to-one functions. Okay, Sophia, could you give me an example that is one-to-one?
Y equals X.
Okay, okay. The simple but it works. Yes, okay. Sakina, an example that is not one-to-one. Simple ones. Okay, okay. X square not. Okay, so if it's one-to-one, we define the inverse function. Let's use it be. And now the inverse. We want to define the function. Is defined in the way that f inverse b. Okay. So we switch the domain to the range and the range to the domain, switch the correspondence, we get the inverse function. This function, the exponential function, is 2 to the x, 3 to the x, they're all one-to-one. But because of this, we can define the inverse function. Okay. F all real numbers to positive numbers. Okay, one-to-one. So we can define the inverse function. The inverse function will switch the domain and the range. This time we use a notation because it's the logarithm. So And the inverse function has the property, the composition recovers the function on different domains. So now we apply this to our exponential and logarithm. Apply it to the, so this means to the logarithm. And this means logarithm to, so two very useful formulas for logarithm. And more generally, have the following formula. Okay, replace this to be. Okay. At least this give very simple, but it give us to compute some logarithms. Let's see some examples. Logarithm 2 to the 8. Okay, Sophia, what's this number?
3.
How do you get a 3?
uh, 2. So it's 2 to the power of a number
Uh-huh. Yes,
equals
yes.
8,
Uh-huh.
and we know that 2 to the power of 3 is 8.
Okay. So now next one, log 3 to the 9. Sakina, what's this? Okay. Yes, yes, okay. Okay. And we can generalize this. We can allow different bases. So a generalization is log p r. So to verify this is easy if set. By definition, this is the same as b to the u equals x. Then x to the r power. We plug in b to the u to the r, b to the u r. So if we take a logarithm, this is reduced to the previous case. If we go over there, we get u r u, and we go back to r. U is logarithm. Okay, that's how we prove our first formula for logarithm. Our second formula, logarithm. So have you seen this formula before? What's this? Okay, and again, we will give a quick proof. So why is this true? So not only, I want you to know not only the formula, but also why. So how to check this? To check this, we introduce two variables. We call this u, we call this v. So u is logarithm bx. This is the same as b to the u is x. V is logarithm b to the y, b to the v is 1. Now let's see what is x1. Xy will be b to the u, b to the v. We apply the laws of exponent b to the u plus v. Then we take a logarithm. We plug in. Okay, we have proved this before. It is u plus v. And then we substitute back to u. Okay, so you know the formula and you know how to verify it. Okay. Okay. And so previously we introduced the natural exponential function. It's a one-to-one to the inverse function. Because this formula function is very popular, we use it so often, we give a special name for it. Okay, so we call it natural logarithmic. So the ln log natural, natural logarithmic function. Okay, now let's check what is ln e. Okay, Sophia, what's logarithm of e?
Um, oh, that's 1.
Okay, how do you get 1?
Uh, so e to the power of 1 is e.
Okay, e to the power of 1 is e because this is logarithm e to the e to the 1. So this is 1. Okay, very nice. Another extremely useful formula, and we use this very often, is the change of basis. Change of base formula. It's very useful. We use this very often. A general base is the quotient. We've seen this before. Okay, now it's very useful. Again, I will give a very short and quick proof. So why is this? So I think that knowing the formula, and if you know the proof of the formula, make it maybe more confident when you use it. Okay, so we don't know what this is. Let's introduce a number, so u. So that. Okay, so from the definition of the logarithm, it's the inverse function. So b could this is the same as Very simple. Now we take a logarithm, the natural logarithm on both sides. Natural logarithm on both sides. Logarithm x, it will be the logarithm b to the u. Okay, this is a logarithm function, the u, the logarithm b. Then we divide both sides by logarithm b. And we so substitute back. We know u is so instead of learning all kinds of logarithm functions with all different bases, it suffices we learn this natural logarithm function. All other ones is just up to a constant. And why this is useful? One application of this is the exponential functions. I go back to exponential functions. Okay. So for this one, we have a formula for it. Let's get the formula. So again, b is positive and not 1. Change of basis. Change of basis. So maybe like let me check. So, how do you prove this formula? Not difficult. Uh, uh, so so it's kind of if we take a logarithm on both sides, see what do we get? If we take logarithm on one side, okay, what do you get? X and b, right? If we take a logarithm of the other side, what do you get? Yes, exactly the same. That's why they are the same. Okay, change of basis. You can see very useful formula, very simple proof. So if we go one step further, we'll be much more confident when we apply the formula. And sometimes we got something wrong, and we can go back to check where it goes wrong. Okay. Uh, Okay, so we have been going on for a long time. We didn't even have a break. So in the future, we will have a break in between. But today we will stop here and ask you if you have any questions. Sophia, start with you.
Hmm. I don't have any questions.